let z equal to x equal to y, x plus y, we have to find the PDF of z, f of z of z. How will we do this? Now, fz of z is this. Now this z is x plus y. So this will be x plus y less than equal to z. Now we make the graph. This would be x plus y equal to z. We want the region x plus y should be less than equal to z. This would be this region. This is x plus y is less than equal to z. Now this we know is double integral fxy xy dx and dy. Okay, now we have to find the limits of y and x. From the graph, the limits of x, we take this strip. So this will be from minus infinity to here is x equal to z minus of y. And the limit of y will be from minus infinity to plus infinity. So we put the limits x equal to minus infinity to z minus y, and y is from minus infinity to plus infinity. Now fz PDF is derivative of fz of z. Now we have to find this derivative. This derivative is found using Leibniz rule. Now Leibniz rule is suppose we have a function fz of z which is integral az to bz fx of z dx. Then fz of z will be derivative of d upon dz fz by z, which will be equal to, we'll take the derivative of this limit first, so it would be d bz upon dz. We'll put this limit into the x, so it will be f bz z minus, again derivative of this limit now, so daz upon dz. We'll put this limit in x, so it would be az z plus, it would be integral az to bz curly fxz by z dx. Using this rule, we'll now find out this. This will be done through fz of z is equal to minus infinity to infinity. These were our y limits. Then it would be partial derivative of, these are our x limits, minus infinity to z minus y fxy xy dx dy. Now we'll use this rule in this. It will be minus infinity to infinity, derivative of z minus y with respect to z is 1. Then we'll do fxy, we'll put z minus y in place of x, so it will be z minus y minus derivative of a z, so derivative of minus infinity will be 0, so this term becomes 0, plus minus infinity to z minus y will be fxy xy upon z dx. this term will also be 0, as with respect to z, this term will be 0. Now, this would be minus infinity to infinity f of, so both this term is 0, this is 0, we are left only with this term, so it would be minus infinity to infinity fxy z minus y y dy. This is the PDF of z equal to x plus y. Now, there are two cases of this. Number one is, if it is given that x and y are independent variables. So we have this PDF of fz of z where our z is given to be x plus y. If x and y are independent variables, then we know that fxy is equal to product of the marginal density, that is fxx fyy. So we'll put this here. When x and y are independent variables, we will get here is minus infinity to infinity fx of z minus y fy of y dy. This is convolution. So we'll get the convolution of fx of z convolution with fy of z. Hence, this is a theorem that if two random variables are independent, then the density of their sum is equal to the convolution of their densities. And if these are not independent, then the density of its sum remains minus infinity to infinity fxy z minus y y dy. And if it's independent, then we have convolution of their densities, that is fxz convolution with fyz. Now we'll have one more problem. When our z is given to be x minus y, this will be similar to that case. First we draw the line. This will be x minus y equal to z. So x minus y less than equal to z will be this area. Again we'll have the limits. The limits would be from minus infinity of x. X limits will be from minus infinity to x equal to z plus y. And we'll have the limits of y from minus infinity to infinity. Again, fz of z would be probability of x minus y less than equal to z. We have got the limits, that is minus infinity to infinity, and it's minus infinity to z plus y. We have fxy, xy, dx, dy. Again here we'll apply Leibniz rule. From Leibniz rule we get we'll take derivative of this limit first, z plus y, so we'll get 1, and then we'll take derivative of this limit, we'll get 0, and then again the total derivative will be 0, so we will be left with only one term, that would be minus infinity to infinity. We have this fz of z, which is derivative of capital Fz of z, and we have minus infinity to infinity fxy z plus y y dy. Now again in this, if x and y are given to be independent, we have the product of their marginal densities, that will be fx of xz plus y into fy of y dy. This would be fz of z. So again, this is convolution of fx of minus z with fy of z. So from here we get two things, that when z equal to x plus y, then we have the sum of the density is the product. When z equal to x plus y, the theorem is that when the random variables are given independent, then the density of the sum when x is plus y equals a convolution of the densities, and again when z equal to x minus y, the convolution will be fx of minus z to convolution of fy of z.